Oh, sorry about that. My other class took a little bit of time to get through. Okay. So yeah, let's begin. Okay, cool. Sorry, I need to code switch here for a second. All right, cool. So just a little bit of housekeeping. We do have our homework assignment all about TS&E plots due tomorrow. And again, if you have any questions, feel free to drop by in office hours. And yeah, what we're going to do today is wrap up with Unit 5, which is talking about all of the different types of commonly used, excuse me, hierarchical clustering algorithms. And so we mentioned that there are two main types of hierarchical clustering algorithms. We have agglomerative hierarchical clustering algorithms that start with all observations apart in singleton clusters. And then we merge until they are all together in one big, grand cluster. And then we're also going to talk about one of the most common types of divisive hierarchical clustering algorithms, in which we start with all observations together in one big single cluster. And then we divide until, theoretically, all of those observations are apart in singleton clusters. Now, the thing here is you can actually be flexible about when you stop that divisive hierarchical clustering algorithm. So, you know, typically a clustering in which all observations are apart in singleton clusters is not, super useful. So you might, for computational reasons, decide to come up with some sort of stopping threshold for the divisive hierarchical clustering algorithms. But what we're going to do is first wrap up with the four main commonly used types of hierarchical agglomerative clustering algorithms. So we talked about one of the key distinctions about, one of the key distinctions that separates all of the different types of hierarchical agglomerative clustering algorithms is how we choose to measure the proximity or the distance, not between two objects, but two clusters. So we talked about single linkage, in which the distance between two clusters is the distance between the two closest points. And then we moved on to complete linkage, in which the distance between two clusters is the distance between the two farthest away points in those two clusters. So what we're going to do next is talk about two other types of linkage functions. But first, we want to talk about some of the potential pros and cons that we might find when using complete linkage hierarchical agglomerative clustering. So I think what I'd like to do first is open up a quick breakout room. It's actually not that many people here. Do I want to do a breakout room? Who wants a breakout room and who doesn't? Is any strong opinions? All right, so if there's no strong opinions, I will open up breakout rooms. Okay, so let's take a look at this data set here. And so basically what this data set visualizes to us is the clustering that we would get when using hierarchical agglomerative clustering, using complete linkage, in which we're at the iteration in which there are four remaining clusters left. So we have the red, orange, blue, and green clusters. That's the only four clusters left in the data set. So what we want to ask ourselves is, will any of the clustering algorithms identified by this algorithm actually identify the three clusters that we would actually want to see? So basically, are we ever going to get a clustering returned from this algorithm in which this is its own cluster? This is its own cluster, this here, and then this is its own cluster. That's the question. Okay, and then think about what would we expect in the next iteration of the algorithm. So basically, what two sets of clusters do we think will be merged next? Okay, so I'll let you take a screen cap of this. I'm going to open up the rooms and yeah, let's discuss, and we'll meet back and discuss in a few minutes. Okay. And you can change your rooms if you'd like as well. Okay, so welcome back. Here, let me post a poll here. So, question is for you all, do we think that the hierarchical agglomerative clustering algorithm using complete linkage will ever be able to identify the three distinct clusters that we're looking for? So basically, will we ever get a clustering with exactly three clusters in which this is a cluster, and this is a cluster? Okay, so please try to submit in the next few seconds. Okay. So looks like most of us say no. And so that is, in fact, the correct answer. So unfortunately, complete linkage is going to fail us in this scenario. So we want to think about what does it actually mean to effectively be able to identify the three, inherent clusters that we're looking for here. So let's think about, what would ideally we want our dendrogram to look like if we're able to, in fact, identify the three clusters here. So this is what we would want to see in a dendrogram, right? So we would want to see basically these two sections of our rectangular cluster merge at a pretty low proximity comparatively. We want these two portions of our other rectangular cluster to merge together next. So let's, if we were at the point in the algorithm which we had 5 clusters left, we'd like for these points to merge and we'd like for these points to merge. And then basically after that, generally speaking, we'd like for the remaining 3 clusters to merge at a much higher level. And basically which one merges first it's not so much of a big deal because, to us, what we can see with our eyes is that they're pretty close to each other. But ideally, in order for us to identify that, these 3 clusters here are in fact meaningfully separated, we'd like for these merges to happen at a much higher level, essentially. So this is what we'd like to see, in which case we would in fact get a clustering with 3 clusters that correctly identified the 3 clusters that we wanted to identify. However, based on what we see here in the current iteration with k equals 4 clusters, this is actually what ended up happening. So basically, in going from the clustering with 5 to 4 clusters, these blue points actually ended up, unfortunately, merging. So we call this a bad merge, in which a set of observations that we wanted to remain apart for a little bit longer actually merged sooner than what we would have liked for them to have done. And then basically because of that, because these 2 sets of points were merged, they're never going to be able to unmerge from each other in order to create a clustering with, which basically looks like this and looks like this, unfortunately. So we'd want to think about what, are we going to get closer to what we ideally might like, or are we, further going to exacerbate the separation of these clusters here in a way that we don't want? So we want to think about using complete linkage. What 2 clusters do we think are going to be merged in the next iteration? So I'll open up a poll for that as well. So which cluster pairs? Red, orange, orange, blue, green, blue, or red, green? Oh, I didn't launch it. Sorry. Here we go. Okay. Try to submit the next few seconds. So someone's asking, why did the blue clusters merge first? There is a distance between them. Basically because the complete linkage distance between them actually was, in fact, the smallest out of all possible pairings that we could have created, essentially. Um, all right, so let me end this poll here. So we'll kind of get a sense as to why these two blue clusters merged when thinking about why the next two clusters merged here. Um, so actually, a bit of a curveball. The red-orange is actually going to be the two clusters that will merge next. Now I realize this is kind of hard, to some extent, it's hard to see that here, but let's take a look at what the distance would be between each of these pairs of clusters here. So you want to remember the distance between clusters when using complete linkage is the distance between the two farthest away points. So for red and orange, it would be something like this. And for something like green and blue, what would be the furthest away points? I think green and blue would be distance something like this, or actually, maybe it would be, no, they're about equal distance here. So it would be a distance of something like this. So we can see that, for instance, this complete linkage distance is a little bit higher than this complete linkage distance. And so actually, the complete linkage distance between red and orange is actually going to be the smallest out of all possible complete linkage distances that you could create between each of these four clusters here. So I do realize this distance here looks somewhat close to this distance, but this one actually does in fact end up being the smallest one here. But basically what we're kind of, so what we ended up seeing here is that, so unfortunately red and orange merged next. And then, so basically, and then what would merge next? Probably green and blue, and then these would merge next. So basically, what we had actually seen in our dendrogram is no particular clustering that actually identifies the three clusters that we're looking for. So this kind of highlights one of the downsides that we end up seeing with hierarchical agglomerative clustering using complete linkage, in that it tends to split large clusters. So this might consider to be a large cluster, and this might be considered to be a large cluster. So we do see that they were unfortunately split to, like they were split up, if you will, in one of the key final merges in the clustering algorithm, in the sense that parts of them were merged together too soon, essentially. So in other words, the clustering algorithm never allows for us to fully have the observations in one of these large clusters completely together by itself. So that's one downside that we end up seeing. Also, a downside of this algorithm with complete linkage is that it also tends to favor spherical clusters. Now, I'll jump to a benefit before I move on to another downside. So one benefit, now this is in contrast to what we saw in single linkage, is that complete linkage tends to be less sensitive to noise and outliers. Okay, so in this context, when we're talking about being sensitive to noise and outliers, what that means is that the dendrogram is not going to basically just pick off singleton outlier points at the expense of not being able to identify the larger main clusters that we're looking for. So a benefit is that complete linkage tends not to do that. Single linkage does tend to do that. However, though, if your goal is to, rather than looking for clusters, if your goal is simply just to look for the presence of noise and outliers, complete linkage is not as good at doing that. So it tends not to be able to identify noise and outliers. Now, again, this is in contrast to single linkage, in which, if you have a data set with noise and outliers, the single linkage dendrogram will basically one at a time pick off these outliers, thereby helping you to identify them. But, the downside is, it does so at the expense of identifying larger main clusters, if you will. So we'll see that in our example. And another benefit of complete linkage is that it's, oops, hold on. It's, this is in contrast to single linkage. It tends to be better at identifying clusters that are not well separated. We saw with single linkage, if you have two or however many clusters that are not well separated, single linkage is not as effective at identifying those clusters. Okay. One downside also is that it tends to be not as good at identifying non-convex clusters. So we already kind of talked about that here. And then another downside, and again, this also applies to all of our common hierarchical agglomerative clustering algorithms that we're talking about, is that it also tends to be not as computationally efficient as an algorithm such as k-means. Okay. All right. Questions on that? Okay. So now we've talked about how basically single linkage and complete linkage their pros and cons tend to be mirror opposites of each other in a lot of ways. So sometimes there might be a scenario. So someone's asking, so complete linkage and single linkage suck at outliers and noise. Well, it depends on what your goal is. If your goal is to identify the noise and outliers, then single linkage can help identify them for you. But if your goal is to basically have these larger clusters that are identified, and you have noise and outliers in your data set, complete linkage will be more robust to those noise and outliers. In other words, complete linkage will be able to find those larger clusters, but it won't be able to really indicate to you what those noise and outlier points are, essentially. So again, it depends on your goals. Do you want to identify noise, or do you want to identify larger clusters? So that's kind of the trade-off, if you will. So single linkage and complete linkage, they have these types of data sets that they're useful for, and they have these types of data sets that they're not useful for. So here's an example of a type of data set that has two downsides. So one of the types of data sets that is not as good for single linkage, and it has one of the types of data sets that is not as good for complete linkage. So for instance, we have this data set here, and basically here are we've represented here the final 6 iterations of the hierarchical agglomerative clustering algorithm using single linkage. So these color-coded are basically our final 6 clusterings here, our final 5 clusterings here. So why do we think that single linkage was not able to effectively identify these 3 clusters here? So basically, why was single linkage not ever able to produce a clustering where this was all together, this was all together, and this was all together? So what's the issue with this data set? Too much noise between the clusters, meaning the smallest distance always read as very close together. So, I would say none of these points here are actually noise. It just so happens, for instance, that, this is a more dense cluster and these are more sparse clusters. But yeah, essentially what we do see here, though, is that these 3 clusters are close to each other. So the issue with single linkage in this data set is that these 3 clusters are not well separated. So we see that single linkage didn't do very well. And so part of the reason is, so what's actually going on here with single linkage is basically all of these points are pretty close to each other. So these points would have all merged together pretty early on. And these points too. So we kind of see this more dense core in these clusters here. And then basically, as the algorithm progressed, clusters that were a little bit further away ended up getting merged together. And then eventually, at one point in the algorithm, there was a bridge that was formed in the center of these clusters here. So basically, this at one point became a cluster, while each of these observations on the outskirts still remained as singleton clusters by themselves. So basically we had a bad merge that happened too soon in the algorithm that merged these clusters together because they were too close. And because of that, we were never able to actually identify all these together, all these together, and all these together. Okay, so we kind of expected that to happen because this is a clustering where the clusters are not well separated. So we might have said, okay, well, let's try complete linkage. We know that complete linkage has sort of this opposite effect. It tends to be better at identifying the clusters that single linkage isn't. But unfortunately, what we can see here is that complete linkage also did not, identify the three clusters that we would be looking for. So all this together, all this together, and all this together. So why do we think complete linkage didn't work for this data set? So what is one of the downsides that complete linkage has for some data sets that we just discussed? Mm-hmm. Yeah, so it tends to split large clusters. So we see an example of that happening here. Now the thing here is actually we were pretty good to go. So everything was still fine at this iteration of the algorithm. Everything was fine at this iteration, and everything was fine at this iteration. Now basically if green and red had merged together next, then we would have actually been able to identify the three clusters that we were looking for. But unfortunately, it looks like, and take note of the scale here, that can be a little bit misleading, but it does in fact look like blue and orange were a little bit closer together than blue and green. And again, the scale is kind of warping things here a little bit. So unfortunately, blue and orange ended up merging next. So basically, we see this example of a data set that has an unideal property for single linkage and an unideal property for complete linkage. So we're going to introduce another linkage function, which basically serves as this middle ground type of clustering solution. So we're going to define average linkage, in which average linkage basically means that the distance or the proximity between two clusters is now defined as the average distance of all pairs of points between two clusters. Okay, so basically that average distance between the clusters, basically we would expect the single linkage between two clusters to be relatively small. We'd expect the complete linkage value between two clusters to be relatively large. And so the average linkage distance is going to be somewhere in the middle between, those two distances that we just described. So because of this, the average linkage hierarchical agglomerative clustering algorithm can in fact strike this middle ground solution, where basically it has sort of this middling effect in the types of data sets that it is good and bad for clustering, essentially. So we'll talk about some of those pros and cons in just a second. But let's cluster this same data set here now using average linkage. Okay, so this agglomerative hierarchical clustering algorithm. So we start again every observation apart in its own singleton cluster. Okay, and then we've also created our initial proximity matrix of all of the clusters, i.e. the distance matrix of all of the objects in the data set. And so based on this initial proximity matrix here, what two clusters would merge first? Again, you actually have two options. So what two clusters are closest together based on what this proximity matrix here says? Yep, so we could either pick 1 and 2 or 3 and 4. So this is a tiebreaker. So let's just say I've set up a tiebreaker rule to pick the pair with the highest object index. So that would be 3 and 4. So in the first iteration, we are going to merge cluster 3 and 4 at proximity 1.12. Okay. And so these clusters merge together. All right, and then we update our cluster proximity matrix accordingly. Okay. And again, I'm just going to focus on the top portion of the matrix, so the bottom portion is redundant. All right, and so 0 and 1, those are simply just the same two singleton clusters, so we already know that that's still 5.1. 0 and 2, we know that that's simply just still 4.27. Then 1 and 2 is still just 1.12. And so what we want to do next is calculate the distance between cluster 0 and cluster 3, 4. So what that means is we are now going to calculate the average distance of every pair of observations within these two clusters. So basically calculate the average of these two distances here. So when we do that, we get an average distance of 4.075. Okay. All right, and then we'd want to calculate the distance between cluster 1 and cluster 3, 4. Okay, so that is going to be the average distance between all pairs of points in the two clusters. It's going to be the average of these two values here. So that would be 4.55. Okay, and finally, we would want to calculate the distance between cluster 2 and cluster 3, 4. And so that would be the average distance of all pairs of points between the two clusters. So that would be the average of these two distances here. So that would be an average of 3.37. Okay. Right. I'm sorry, this is a little bit sloppy. Not very good at writing on a tablet, unfortunately. Okay, so that is our updated proximity matrix. And so the next step is to figure out what two clusters based on this proximity matrix are closest, or in other words, what two clusters we should merge next. So what two clusters are merged now? Yep, it's 1 and 2. So we see that cluster 1 and cluster 2 are now the two closest clusters. We merge 1 and 2 at proximity 1.12. Okay. So now these are both together. Okay. And so next, we update our proximity matrix. So 0, 1, 2, 3, 4. Okay. And so 0, hold on a second. So 0 and 3, 4, we've already calculated that above. That hasn't changed. So that's still 4.075. Okay. So next, what we need to do is calculate the distance between cluster 0 and cluster 1, 2. So we would find the average distance between all pairs of points in these two clusters here, or take the average of these two values here. So we would get 4.685. Okay. And we would also calculate the distance between cluster 1, 2 and cluster 3, 4. And so that would be the average distance between all pairs of points in these two clusters here, or the average distance of these values. So when we do that, we get a proximity of 3.913. Okay. All right, so we have our new updated proximity matrix of clusters. They move on to the next iteration. And so, based on this proximity matrix, what two clusters are closest and merge next? Mm-hmm. Okay. Yep, so the two closest clusters now are 1, 2, and 3, 4. So we merge cluster 1, 2, and 3, 4 at proximity 3.913. Okay. And so those two clusters now merge together. All right. And we update our final proximity matrix with 0 and 1, 2, 3, 4. Okay. All right. And last but not least, we now need to find the proximity between cluster 0 and cluster 1, 2, 3, 4. Okay. So that means we calculate the average distance between all pairs of points in these two clusters here, or calculate the average of this distance here. And so what we get is an average distance of 4.36. All right. And so last but not least, we merge the two remaining clusters. So we merge cluster 0 and cluster 1, 2, 3, 4 at proximity of 4.36. All right. And we end the algorithm with all observations together. Yeah, so someone's asking about what distance metric was used. So yeah, we used the Euclidean distance to calculate the initial proximity between all objects, in the data set. Now, for instance, if you had wanted to use a different distance metric to measure the distance between objects, then you could have, the only thing that would change is how you constructed this initial proximity matrix. So that would be, you could use like the L1 norm, for instance, but then basically every other step would be the same because your, subsequent proximity matrices of clusters would be based off of this L1 norm proximity matrix. Okay. All right, so to put it all together, let's construct our final dendrogram. Okay, and so on the y-axis, we have the proximity. And on the x-axis, we have our labels. Okay. And so again, 3 and 4 merge together at a proximity of 1.12. And so do 1 and 2. And then 1, 2, 3, 4 are going to merge at a proximity of 3.913. All right. And finally, 0 merges with 1, 2, 3, 4 at a proximity of 4.36. And so that creates our average linkage dendrogram. All right. Cool. Any questions on that? Okay. So let's think about some of the benefits of, using average linkage. So like we mentioned, average linkage can be beneficial if, for instance, your data set has some of the inherent unideal properties for single linkage, and it might also have some of the inherent unideal properties for complete linkage. So average linkage might be a solution for you because it strikes a middle ground solution or set of results between the pros and cons of single linkage and complete linkage. So for instance, average linkage is more sensitive to noise and outliers than complete linkage, but less so than single linkage. On the other hand, though, if your goal is to identify noise and outliers, and you don't really so much care about clustering, you might say it is less able to identify noise and outliers than single linkage, but more so than complete linkage. Okay. And so one of the downsides that we saw with complete linkage is splitting large clusters. So it is less likely to split large clusters like complete linkage, but it is more likely to split large clusters than single linkage. Okay. And so we saw, one of the benefits, for instance, of single linkage is that it's really our first algorithm that's able to identify non-convex clusters. So one of the downsides of average linkage is that it's less able to identify non-convex clusters than single linkage, but it is more likely to identify non-convex clusters than complete linkage. Okay. Also, one of the downsides of single linkage is that it's not as good at identifying unwell separated clusters. So it's more able to identify non-well separated clusters than single linkage, but less able to identify these types of clusters than complete linkage. Okay. Goldilocks and the 3 linkage algorithms. Yeah, maybe. So, and the thing here that you want to remember is that, average linkage, even though it strikes this middle ground solution, it may still suffer from its own performance issues as well. So we're going to see a situation in which single linkage doesn't work out very well for our country's data set. Complete linkage also doesn't work out as well for our country's data set, but average linkage also is not going to work out well either. So there's this commonality in the linkage function for single, average, and complete linkage, and that they were all using a a graph-based notion of similarity. Or in other words, we were comparing pairwise distances of points in the two clusters. So we're going to deviate from this graph-based notion of cluster similarity to something very different. So another common linkage function that's talked about is what we call Ward's linkage. So there's a general way to calculate Ward's linkage, and then there's a very common way to implement Ward's linkage. Someone's asking here, does there exist a median linkage, kind of like how there's a k-means? Yeah, so we are just getting to that now. So basically, you can actually think of Ward's linkage as kind of like a k-means focused linkage function. So the general definition of a Ward's linkage proximity between two clusters is it's defined as the change in objective function value that we would get when we merge the two clusters. And when we talk about, when we're talking about the objective function, this is basically just, whatever function your clustering optimization problem is seeking to minimize, right? So for instance, when we introduce k-means, right, we're trying to minimize, our objective function that we're trying to minimize is inertia. When we talked about k-metoids, the objective function that we were trying to ultimately minimize was the distance of all points to their closest metoid. So naturally, the most common objective function that we use for, or to define Ward's linkage is that k-means based inertia objective function. So generally speaking, unless somebody specifies otherwise, what we tend to think of Ward's linkage is the change in inertia that we would see if we were to merge the two clusters in question. So Ward's linkage tends to take a lot more time to basically go through manually. So we're only going to go through the first iteration of Ward's linkage here. So again, we're going to start with all observations apart as singleton clusters. Okay. And so, given that we're going to be thinking about the change in inertia that we might expect to see, for instance, if we were to merge two of these clusters, let's first think about, well, what is the inertia of this original clustering here? So this clustering with 5 clusters, what is the inertia? So each of our, yeah, exactly, you got it. Someone sent me a direct message, but yeah, you want to think about, well, where's the centroid of all of these clusters here? Well, the centroid, because each of these clusters only has one point, is simply just the point itself, right? You want to remember inertia is the sum square, or the sum of the squared distance of each point to their assigned cluster centroid. So distance between each point and their respective centroid is in fact 0. So therefore, the inertia of this entire clustering is 0. Okay. All right. And so that's going to be the case for any data set when we start out this algorithm. Okay. And so to calculate the new proximity matrix, what we would want to do next is we'd want to think about what we might expect to see. We basically want to, calculate the inertia that we would get, the overall clustering inertia, if we were to merge each potential pair of clusters. So for instance, if we were to merge 3 and 4, then we want to think about, well, where's the new centroid of that cluster? So that'd be right here. And then we would want to approximate the new inertia of this resulting clustering with 4 clusters. So we basically take these two distances here, square them, and add them up. Okay, so we would get, the new resulting inertia of that new clustering with 4 clusters that we would have created would have been 0.625. And so the final step to calculate the actual proximity matrix would be not to use the inertia of the would-be clustering that we would get if we merged those two clusters, but to calculate the change in inertia. So for instance, the distance between cluster 3 and cluster 4 in our Ward's linkage proximity matrix above is this new clustering inertia of 0.625 minus the old clustering inertia of 0, basically. So basically, all of these new inertia values would be subtracted by the 0 of the old inertia. Okay, and so based on this proximity matrix here, next question is, what two clusters would be merged next? Based on this. So basically, which one has the smallest distance here? So again, you've got multiple options. You can pick this one or this one because these are the two smallest values. So yeah, so we could say that, for instance, clusters 3 and 4 merge at proximity 0.625. So these two clusters, 3 and 4, would permanently merge. And then we would move on to the next iteration in the algorithm. Okay. So this is going to take a lot longer, but that's the general idea of Ward's linkage. Any questions on that? Okay. So quick benefits of using Ward's linkage is it tends to be effective at identifying spherical clusters. Okay. But the downside, and maybe you can anticipate this, is that we're using the same objective function that we used in k-means. So in other words, Ward's linkage is carrying with it the same assumption as to what defines a cluster. So it's carrying that prototype-based definition of a cluster. So which means it's going to be better at identifying the types of clusters that k-means is also good at identifying. So because Ward's linkage also uses inertia to evaluate clustering effectiveness, just like k-means, it also tends to be best at identifying the types of clusters that k-means is better at. So what does that entail? So what are some of the ideal properties of a data set that k-means is able to identify the clusters in? So I will say, because this is a 430 set, this is like basically a 400 level class, there's no fixed amount of content that I have to get through. So the more time I spend waiting for responses means we don't get to as much content, unfortunately. It's a little bit of motivation there. So what is one ideal property of k-means? Yeah, okay. So the clusters in which they have the same density, they're well separated, Same number of observations in the clusters. They're all spherical. Okay. And then also you want to remember, k-means, as well as Ward's linkage, as we're going to see, tends to be more sensitive to noise and outliers. Okay. All right. So there's some pros and cons of Ward's linkage. Any questions on that? All right. So I'm going to return back to divisive hierarchical clustering probably on Tuesday, because I don't think I'm going to have enough time for this entire unit. But I want to get to the application here. So in the application, we're only going to focus on agglomerative hierarchical clustering algorithms. So you want to remember that we have this countries data set in which we'd like to cluster these 9 demographic attributes for each of the countries here. And so you want to remember that our overarching research goal is to find a clustering in which basically no observation is by itself in a singleton cluster. So ideally, we'd like to use this clustering of country to make some sort of international decisions based on like what cluster a given country falls into, basically. So if for instance, like international climate change negotiations tend to group countries together as such, and they use that to suggest what type of contributions they should make towards mitigating greenhouse gases, for instance. So we want to make sure that when we're clustering this data set, even if it meets even if it has high performance based on one of our unsupervised clustering evaluation metrics, we still want to keep that goal in mind, right? So let's also do a little bit of pre-processing here. So let's take our 9 numerical attributes and let's describe them. So let's calculate some basic summary statistics. So for instance, calculate the standard deviation of each of those attributes here. So what do we think? Should I scale this data set first? So let me ask a poll. So based on what I'm seeing here, should I scale the data set, or do I need to scale the data set? Okay. Yeah. All right. So yeah, so the answer to this question is it kind of depends. So you'd want to ask yourself, do you want each of your numerical variables to contribute an equal contribution to the nature of the clustering structure that is identified? Or are you okay with perhaps one or more particular variables dominating the nature of the clustering structure? So if the answer is no, then you should definitely scale these variables by using for instance, z-score scaling like we mentioned in the homework assignment. So for instance, we see that income has a very high scale in comparison to the other variables. So what that means is that if you don't if you don't scale your variables first, then it's highly likely that income especially is going to dominate the clustering structure that the TS&E plot identifies, as well as your algorithms. So, it's possible that, maybe income actually doesn't contribute a whole lot to the clustering structure. And so if it was dominating the results, then you might not actually be able to see the more, the clustering structure that's, contributed by some of the smaller scale variables. So someone's asking a question, is there ever a disadvantage to scaling a data set? So yeah, so it might actually be possible, like you might actually want some of your variables to have a higher scale, or in other words, to have more of a say on the nature of the clustering structure. So for instance, if you see that like you have a data set here, like, and you have 2 variables, and like one of those variables exhibits a relationship that's a little bit weaker in structure like this. So maybe say you have like this, this XY variable here. And then let's just say you have this other, this other variable z in which, you see this scenario in which basically almost every observation is a 1 and very few observations are like a 2. And so you might ask yourselves, well, like, is this, I mean, this is a huge gap here. So basically, if all variables are considered the same in the clustering structure, even, so basically, even if X, Y, and Z have the same scale, because the gaps that exist in the Z variable are so large in comparison to the gaps that exist in the X and Y, even if you scale those variables, Z's gaps are going to have a very dominant, a strong dominance on the nature of the clustering structure that you see. But it might actually be the case that, maybe you don't actually want these gaps to be as highly considered, because maybe the gapping that you're seeing here perhaps is not as meaningful as perhaps the gaps that might exist here. So someone's asking, in this case, is Z categorical? So not necessarily. So what we're taking a look at in our current homework assignment, especially with the TS&E plots, is, what can happen to your clustering structure if you're not necessarily dealing with a categorical variable. What happens to your clustering structure if you're dealing with like a discrete variable with just a few distinct values? So this would be a scenario like that, in which, like, you have this discrete variable, which really, in a meaningful or in a practical sense, like, it might be the case that these gaps are not actually super meaningful to the purpose of your cluster analysis, but these gaps nonetheless might be detected by many of your algorithms as meaningful. So therefore, what you might want to do in a scenario like this is perhaps downweight the scale of Z in comparison to X and Y, because maybe you want to focus more on, the gaps that exist here. So that'd be one scenario that you could think of. But that's a good question. Okay, I need to move on here. So because we don't want our results to be dominated by any one particular variable, we will scale our variables using z-score scaling. So basically, we will take each of our columns in the data set and we will subtract its respective column mean and divide by its respective standard deviation. Okay, and again, when you use the standard scalar fit transform function, it returns a NumPy array. So I like to kind of, just deal with pandas data frames for the most part. So I will put that NumPy array back into a pandas data frame, and I will give it the same column names that I had before. And so this is my overwritten scaled pandas data frame. Okay, and I might decide to re-add the, country variable back to this, this additional data frame that I've created. Okay, all right. So now let's take a look at this scatter plot here. So because you want to remember that clustering is a more sophisticated type of descriptive analytics technique, but it's always a good idea to explore basic descriptive analytics techniques before performing cluster analysis, because it can give you insights, for instance, as to what types of clustering algorithms may be more or less useful for your research goals. So of the 4 linkage functions that we discussed, based on what we see here, do we think that one of those linkage functions is not going to give us great results based on what our research goal is? So the question is, what are we noticing here first? Yeah, well, so it's hard to really see the clustering structure yet. So just because we don't really see any clustering structure in the, every set of scatter plots doesn't mean that one doesn't exist. So we'd want to consult the TS&E plot for that kind of assessment. But this is something that we don't need a TS&E plot to see. So for instance, I'm noticing that I can see quite a few outliers, right? And so given that I want to cluster a data set with large clusters, so basically given that I don't want to have any singleton outlier clusters, which one of my hierarchical agglomerative clustering algorithms should I be the most skeptical of based on what I see here? So which one of my algorithms did I say is sensitive to noise and outliers? Yeah. So I should be wary about using single linkage. All right, but let's actually test that there. But we want to be on the lookout for that based on what we've seen. Okay. And so we've already discussed the TS&E plot for this data set. So this is all things that we've seen before. And so it's harder to see, have a clear sense as to whether there's a clustering structure yet based on based on these low perplexity values. But as we increase the perplexity value, we're starting to see somewhat of a pattern, a consistent pattern with regards to shape, separatedness, so on and so forth. So usually, after examining multiple TS&E plots and seeing multiple similar patterns for evidence of a clustering structure, I usually select just one TS&E plot to kind of use throughout the rest of the analysis. I'll usually I'll pick the TS&E plot that best exhibits these common clustering structure elements that I'm seeing across multiple perplexity values in multiple random states. So for instance, the perplexity of 30 in a random state of 8 typifies a lot of these common clustering structuring elements that I'm seeing, for instance. So for instance, I'm seeing evidence, we've kind of already discussed this already, of perhaps 3 distinct main clusters that are not well separated, and perhaps some evidence of some subcluster relationships within, some of these main clusters here. Okay. And you want to remember, TS&E plot does not show me outliers. So it is possible that there could be outliers in this data set, and I did see outliers in my scatter plots. But as of right now, I'm not really seeing any strong evidence of outliers in the TS&E plot, which is I wouldn't expect to be able to identify it here. Okay. So also keep in mind, maybe this middle cluster might actually be considered to be a large cluster. So we want to be on the lookout for potentially like complete linkage, like splitting this larger cluster. Okay. So examining the TS&E plots can also give us a sense as to what your best bet might be for a particular clustering algorithm. But it's always a good idea. I mean, if you're able to try out multiple clustering algorithms, it's a good idea to consult with multiple clustering algorithms because they can, in essence, reveal different aspects of the data set, which again is our overarching goal for an unsupervised learning analysis is to learn as many useful insights as possible. So what we're going to do is we're actually going to consult all of our 4 hierarchical agglomerative clustering algorithms. And we're going to try to see what do they tell us about this data set here. And luckily, now that we know TS&E plots, the TS&E plot is going to basically give us this additional level of corroboration or indication that the resulting clusters are in fact what we are looking for, or in other words, best meet our research goal. Okay, so let's start with basically just a naive implementation of a hierarchical agglomerative clustering algorithm. So we discussed that all hierarchical agglomerative clustering algorithms start with an initial proximity matrix of the objects in the data set. So this is where I create my initial proximity matrix, and this is where I can stipulate what object distance metric that I want to use. So usually I just tend to use Euclidean distance unless I have reason to believe I should use something else. So this creates my initial pairwise object distance matrix. And then to actually perform the hierarchical agglomerative clustering algorithm, I use the linkage function. And so this is where I stipulate the actual linkage function that I like to use. So I'm going to start with single linkage. Okay. And basically what that creates is this linkage function object, which is not super, visually useful by itself. So basically this is a encoded NumPy array that tells us when and at what level each of my pairs of observations or each of my observations should link with each other. But to get the nice visually appealing dendrogram, I can take that linkage function object and I can put it in my dendrogram function, okay? And I can stipulate some parameters, so not all of these are needed. So for instance, I might want to change the orientation to right. In addition, I might choose to label the observations on my y-axis now. So I want to label the observations by the country because I think that's going to be useful and informative. And for instance, if I'd like to resize the plot, which oftentimes it's, you get better visualization if you resize your plot first with these height and width specifications. So you can resize your plot by using the axis parameter here. Okay. And so this is the first dendrogram that I end up getting by using single linkage. Okay. So what do we think I'm going to ask a poll. Based on the explicit research goals that I've stated at the beginning of the analysis, do we think that this dendrogram is going to be it? So do we think that some of the clusterings that I could pick out in this dendrogram are going to be useful for my overall research goal? Okay, so try to submit in the next few seconds. Okay, so we're saying no. So yeah, based on what we see here, we can all, yeah, I also agree that this is not going to meet our research goals. So let's examine the first clustering that we could extract, or in other words, the clustering that we would get with two clusters. So I draw my vertical line in this case, and I follow each of the branches down to their corresponding observations on the y-axis. And so what I end up seeing is two clusters, right? One cluster just has Nigeria, and the other cluster is literally every other country. So I can see if I just look at my first clustering with two clusters, then I've basically created a clustering that does not actually find any meaningful, well-balanced cluster sizes, if you will. And I also mentioned I don't want to have a clustering result like that where it's just one country by itself, because that's not as useful towards my research motivation. So maybe I'll go a little bit further down in the tree. So I'll find my clustering with three clusters. So I see my three intersections here, but unfortunately, if I look at the clustering with three clusters, then the clustering that's created is one with Nigeria by itself, one with Luxembourg by itself, and then every other observation in another cluster. So again, this is not really helping. So it looks like, and we can basically see as we go further down the tree, it looks like what is happening here is that this dendrogram is not really identifying any meaningful, well-balanced clusters. But my suspicion, what it's doing, is that it's basically one at a time picking off these outlier observations as their own singleton clusters. So, if my goal was to identify the existence of potential outliers that maybe I hadn't been able to detect through other means, then this is actually pretty cool. This allows for me to identify outliers that I might not have known about, that I might not have been able to see just by looking at a two-dimensional scatter plot. So let's actually check whether these 2 points that we've picked off so far are in fact outliers or not. So basically we use the dendrogram function to construct the dendrogram. But if you'd ever like to extract just a single clustering or a single partition-based clustering from the dendrogram, you actually need to use a different function. So we need to use this agglomerative clustering function. For instance, if we wanted to identify a set of cluster labels given to the clustering with let's just say 2 clusters that is found in that dendrogram. So you'd specify the number of clusters and the clustering that you'd like to pick off from the dendrogram. And you also need to select the distance metric between the points that you're considering, as well as the linkage function. Okay. And so basically I've set up all of my stipulations here, but because I actually haven't run a fit or a fit predict function, I've yet to run the algorithm or yet to generate the results. So when I run fit predict with this agglomerative clustering object that I've just created, what that returns is a corresponding set of cluster labels here. Okay, so we can basically see that Nigeria received its own cluster label, and then every other observation received a different cluster label. Okay. And so, for instance, if we wanted to examine the clustering with 3 clusters in that dendrogram, we could use that same function, this time looking for 3 clusters. And run the fit predict algorithm again on my X data frame. And this creates this different set of cluster labels for the clustering that corresponds to 3 clusters. So I can see here again, I've got 1 singleton cluster of Luxembourg, 1 for Nigeria, and then 1 for everything else. Yeah, so someone's asking me a question, is hierarchical clustering non-deterministic? Is there any randomness in scikit-learn functions? Yeah, so take note, there was no element of randomness in how we were constructing these dendrograms here. So the hierarchical agglomerative clustering algorithms that we've described, at the very least here, are deterministic in nature. So they'll always give you the same results. Okay. And so basically, if I were to color code by those cluster labels for the clustering with 3 clusters that I just created here, as I would expect, it's not immediately obvious, right, that these points are outliers from the TSNE plot. And again, TSNE plots don't tell you if a point is an outlier. So if I wanted to actually, or if I wanted to try to corroborate that these points were outliers, I could color code my pair plot by the cluster labels. And so it just so happens that I can in fact verify that those outliers that were being, or those singleton clusters that were being picked off are in fact outliers, because I can see it with these 2-dimensional scatter plots. But again, take note that not all outliers present themselves when looking at just 2 variables. Sometimes only an outlier will make its outlier status known when looking at, for instance, the relationship between 4 variables, which is something that we can't verify ourselves. So this is why a single linkage dendrogram, while it might mess up it might not be useful for cluster analysis when you have outliers in your data set. It can, in fact, be useful, at the very least, when it comes to telling you that you do have these hidden outliers that you might not have known about. Okay. Oof. Okay, I have run out of time. Shoot. Okay. I'm sorry to do this, guys. I might have to add on an additional 10 minutes of content after this class, basically. But basically what we're going to do is we're going to try out each of our 4 respective linkage functions. We're going to create 4 distinct dendrograms using the using the code that we described above. And we're going to use this to help us select which dendrogram as well as which clustering is going to best help us meet our overarching research goals, essentially. Okay, so 10 to 15 minutes at most. I'll send you guys an email when that extra video content is ready today, essentially. But yeah, we'll stop there. I will stop recording. And